and probably will not return in our lifetimes. I showed you that chart of all the sunspot cycles laid on top of one another, where cycle 24 minimum was the lowest ever. There were 266 spotless days in 2008. I'm sure we all remember that. For people that operated at 160, it was amazing. Zone 18 over the pole, day after day after day. It was pretty amazing. And then we had this sudden, unexpected peak that occurred in November 2011, and people were thinking, wow, the good times are back. And then it went clunk early by the spring of 2012, and last year we were in these doldrums. And then in October, the same thing started to happen that happened in 2011. But unlike 2011, it's been sustained, not at this peak level way up here, but it's only declined to about here for the last few months. So this second peak is sustaining itself. Well, you might say, and I'll get off the main topic of the presentation just for a moment. People will say, well, but 10 meters isn't open every day anymore. What's happened? And 12 meters is pretty dead too. That is a normal seasonal change. That has nothing to do with sunspots. It's not March, April anymore. We're now getting into mid to late May, and we're getting into the normal change in propagation patterns as we approach the summer, and the focus of long-range propagation shifts to 20, 17, and 15 meters, and 12 and 10 meters go into their normal seasonal decline, having nothing to do with sunspots. Okay, 100 years ago, sunspot cycle 14. This was another sunspot cycle with two peaks. And sunspot cycle 14 had two peaks spaced 2 years, and the second peak was about the same size, more or less, of the first one. And people were looking at the statistics of sunspot cycle 14 and saying, hey, maybe sunspot cycle 24 will do the same thing. And everyone was hoping, well, let's hope for another peak out here. Well, why are there two sunspot cycle peaks? There often are. And the reason is the northern hemisphere of the sun, typically the sunspots in the northern hemisphere peak at a different date and year of the sunspots in the southern hemisphere of the sun. They typically do not peak at the same time. I don't know that anyone knows the reason for that, but if you look at data going back hundreds of years, that's true. And here's some of the data going back to 1945. Southern hemisphere in red, northern hemisphere in blue. And you can see for almost all of those years, there's about a 2-year separation between the peak of the southern and the northern. And you can find all kinds of interesting statistics if you want. Here's a year, 1957, that big peak. The northern hemisphere was the one that produced all that activity in 1957. And here's another one where the second peak was bigger. This is very similar to our experience. The second peak was much bigger than the first. The last sunspot cycle 23, the two peaks were about the same. Oddly, the southern hemisphere had two peaks. And you can find all sorts of statistics. And when this particular chart was produced was produced just as the northern hemisphere peaked and the southern hemisphere was weak. But the two hemispheres, the sunspots count never peaks at the same time. We'll take another look at sunspot cycle 14, more detail than the other chart showed, and very similar to what our experience has been in sunspot cycle 24. The southern hemisphere started to increase in this sunspot cycle 14 about a year after the northern hemisphere declined. That's very similar to what our experience was. But don't get too hung up on these statistics. We're looking at a star that's billions of years old over 400 years of history. And we'll take a look at the last two sunspot cycles. So this was sunspot cycle 22, and sunspot cycle 23, and a similar thing happened. 22 was more like this sunspot cycle, where the second peak in the southern hemisphere was bigger than the first. But these were much bigger sunspot numbers than we have now. But nonetheless, the southern hemisphere was much bigger. Okay, so let's look at something really different in terms of long-range prediction. During the last sunspot, about the time of the last sunspot cycle, some new theories about the relationship between the magnetic field on the sun and the appearance of sunspots started to emerge in the scientific community. And some of the most accurate long-range predictions of sunspot cycle 24, the current sunspot cycle, were made during the preceding minimum, about 4 years before. So for those of you that remember, so this sunspot's first peak occurred in 2011. So around 2007, there were predictions that went all over the map. You could pick your favorite prediction. There were people predicting the biggest sunspot cycle since 1957. I think there might have been even some predicting even bigger than that. And there were some that said, well, it'll be about the same. And there were others that said there weren't going to be any sunspots at all. And you could find everything in between. Well, there were some scientists that used a particular scientific method who, for sunspot cycle 24, proved to be very accurate. And it was the people that produced the forecast that I showed you from that NASA site. Now, I can't stand here and tell you that the method that they used for sunspot cycle 24 is necessarily going to be accurate for 25. But going back in time using that method, it would have predicted the previous sunspot cycles for the last 100 years with good accuracy. We don't know if it's going to be the same for 25. It's just 10 years out of billions. But it'll be interesting to watch. So here's what the prediction method is that was used accurately for sunspot cycle 24. And the observation is that there's a theory that's called the solar dynamo theory. And that is basically that sunspots are nothing but eruptions on the surface of the sun caused by intense magnetic activity that extends deep below the surface of the sun. And we're just seeing symptoms of that with these eruptions that occur on the surface. And the dynamo theory says that the transport mechanism involves the movement of magnetic fields that are easily observed by measuring the magnetic field intensity in the polar regions of the sun. We now have instruments on Earth. Stanford University out in California has an observatory that can very accurately measure the magnetic field intensity on the sun in the northern hemisphere and the southern hemisphere, and they publish records of their readings every 2 weeks. I'll show you their website in a minute if you're interested in watching this. It's kind of like watching the stock market. It's just data. You don't really know what the data means, but it's there. But here's some plots, and this is the measurements made at Stanford University of the north and south polar magnetic fields. So these are magnetic. It's not geomagnetic, of course. It's solar magnetic in the area of the north and south pole, those regions, and it's measured in a measurement called, the unit is microteslas. So on this chart on the vertical axis, these numbers are pretty small numbers compared to the peak. There's neutral, 0 field strength right here, and that dark black line is 0 field strength, and any measurements that cross this line are called a field reversal, when it goes from negative numbers, and this is kind of counterintuitive the way this is shown. The negative numbers are up here, positive numbers are down here. So the measurements of the north polar magnetic field back in early 2012 started as very weak numbers. Before that they were up here. So this chart continues kind of looking like that. And then in June 2012 the northern hemisphere changed its polarity and went from negative magnetic field strength to positive and slowly increased. And look what happened after 2013. Surprise. Started to decline again. And right now, this chart was produced in about March. And if you go to the Wilcox Solar Observatory website and you look at the data for the last couple of months, another field reversal has occurred. And very, very weakly, these numbers are back up in this region, up here. Nobody knows what's going to happen up here. But I think the only important thing is that these numbers are still very weak numbers. And the southern hemisphere started out in that same period. So the northern hemisphere, which had, we all know by November 2011, had large sunspot numbers. So the sunspot numbers were high in November 2011. The magnetic field intensity in the North Pole, where all these sunspot, all of the sunspot intensity was in the northern hemisphere. The sunspot peak occurred here for the northern hemisphere, and the polar magnetic field strength reached zero at about the same time, a few months later. While the southern hemisphere, which was very inactive in terms of sunspot activity, still had pretty high magnetic field intensity in the northern hemisphere, and that steadily declined. And it reached zero in June 2013 and has continued to increase, but it's starting to flatten out here. So it's not reaching very large numbers. So there are two things that are visible in this data. Nobody knows what it means yet. But there are two things visible here, and that is that the field strengths are still very low magnetic field strength. And the other thing is that the polar field reversal has occurred, which is usually an indicator that we've passed solar maximum when both of these field reversals happened. This first field reversal of the northern hemisphere happened in June 2012, and the second one of the southern hemisphere occurred in June 2013. So almost always this is an accurate indicator that the solar maximum has happened. And the other precursor data, and we won't be able to use this, the scientists won't be able to use this for predictions for at least 2 years, maybe 3. But what they'll be looking at is whether these intensities build up again and get up into numbers in the order of 100. If the magnetic field intensity is high at solar minimum, that is a precursor indicator of high sunspot numbers in the next maximum. And that's how that prediction was done. What they observed in the last sunspot minimum back in 2007, they observed that the magnetic fields in the polar regions of the sun were unusually weak. So they looked at the unusual weak magnetic fields compared to historic data, and their prediction as a result was that the dynamo effect on the sun was weakened, and that sunspot cycle 24 would be a historically weak cycle. And they were right. So these same scientists will look at this data, and if these as we approach the next minimum, as we get closer to 2020, if these numbers are double-digit numbers instead of triple-digit numbers, or even worse, if this continues to flatten out the way it's happening right now, then we might be leading to an even lower sunspot maximum sometime in the middle 2020 region, 11 years from now. So this is the prediction method that was used: magnetic field intensity in the polar region. And in about 2 years, maybe we'll have something to look at, 2 or 3 years maybe. So let's look at what's happening now with sunspot activity. This is the sunspot number on the left side. And here's what was going on in the northern hemisphere. We had a peak back in November 2011. It was up about here. And then the numbers declined and stayed kind of flat. And then towards the end of last year, as we were approaching this second peak, the northern hemisphere started to weaken even more. So the northern hemisphere isn't a big player in all of this good sunspot activity that we've enjoyed. The main activity has been in the southern hemisphere. And the peak, right up until now, occurred in February of this year. And, nobody knows what's going to happen for the rest of this year, but inevitably, we are sometime this year going to start the inevitable decline to the sunspot minimum in 2020. But whether the peak has already happened, or there might be some surprises again in store later in this year, nobody knows. Nobody expected this. This was a big surprise, and nobody knows if it might happen again out here later this year. But the other thing we know is there is inevitably a sunspot cycle, and inevitably that peak is going to occur around 2020. So some point, this question mark is going to start being down here. So in terms of planning, that's why we look at long-range predictions. What about planning? Pretty good chance that we're going to have some very good 10-meter propagation again during the next fall, winter, early spring season, 2014, 2015. So if you like to work DX or contest on 10 and 12 meters, this might be your last really good opportunity to do this for many years to come. So don't miss the opportunity to improve your antennas for 10 and 12 meters. Those are small antennas. Don't miss openings that might occur. Don't say, gee, I didn't expect 10 meters to be good because the sunspot cycle is on the decline. Pay attention to 10 meters this coming season. It might be your last chance for a long time. Okay, so there's more good news. Solar cycle 24 has been a weak cycle. And as a result, the degradation of 160 and 80 meters that usually occurs with sunspot maximum has not been nearly as severe with this cycle as it has normally been. So those of us who enjoy the low bands and DX contests, or for DXing in general, have had a pretty good experience on the low bands. This last season was noticeably worse than the other seasons in the few years before. So we could definitely see that as 15, 12, and 10 meters got much better during this last contest season. 160 was worse than the couple of years before, but not terrible. Well, there's another trend that occurs in this data, and that is during the decline of the sunspot cycle, which we are about to enter, probably by late this year. Normally, the A index increases moderately during those first few years of the decline of the sunspot cycle. So this somewhat degraded 160 meter and 80 meter propagation we've had this last contest season, pretty likely that that decline is going to continue for a couple more years. Pretty likely. If historical data holds true, and it generally has held true, that the first years of the decline of the sunspot cycle are not good years for the low band. Okay, long-range estimates. Very, very few scientists are going out on a limb, because it's a dangerous thing to do this early before the next sunspot cycle. But boy, there are some undeniable trends that you look at. I told you about the Gleisenberg cycle, and you can see that 80-year cycle in this data. You can see this incredible modern maximum that many of us experienced from the 1950s through 2000. And now there seems to be a kind of undeniable trend here. And this particular scientist, there's his website, he has made an estimate, not a prediction, but an estimate that sunspot cycle 25 could be the weakest since the Dalton minimum 300 years ago. So this is not my prediction, but it's something to watch for in the next 2 or 3 years. This is what's possible in terms of our future. Okay. This is my prediction, and it's and all I'm really doing is saying I tend to trust this NASA site. This is what they've predicted. This is 2015. This is the range of possible outcomes in their forecast. This is their most optimistic forecast. This dotted line is their least optimistic forecast. This is their most likely forecast. Notice that this data tends to track it pretty well. Next contest season is likely to be pretty good. Probably not as good as this last season, but plenty of opportunity for 10-meter propagation, nighttime propagation on 20, propagation well into the evening on 15 meters. So be prepared for another good season and what might be the last one of our lives. Might be. So I think that's the end. Yeah, that's the end of my presentation. So are there any questions? Oh. Thank you for reminding me about that, Bill. I enjoy 6 meters. It's a lot of fun. Does anybody here operate 6 meters? Was anybody active last weekend? How was it? Tell us about it. Wonderful. That's right. It's amazing. Absolutely. And that was F layer, partially. That was transequatorial propagation, coupled into the northern latitudes, probably with sporadic E, because we're in the sporadic E season. 6 meters is an amazing band, and last weekend was incredible. For those that don't operate 6 meters, on Saturday, normally transequatorial propagation, it's a mode of F-layer propagation, normally peaks in the afternoon, starting around 2 o'clock in the afternoon, and the peak of transequatorial F-layer propagation on 6 meters and even 10 meters occurs from about 2 in the afternoon until about an hour or two before sunset, depending on how intense the ionization is. So at about 2 o'clock in the afternoon on Sunday, ZD7VC on St. Helena Island, who's been on 6 meters for 14 years, for the first time worked into the United States and worked 55 stations in the United States on 6 meters. So anyway, I've got 10 acres, so it took a while. So I missed that, but that wasn't all that I missed. So then when that opening ended, and it was kind of a weird opening, it was kind of focused in different parts of the country for a few minutes at a time. Some areas of the country enjoyed propagation that lasted for more than an hour. Other areas had only a few minutes. So that one went away. And then another station that has only worked 1 or 2 QSOs in the United States had a similar opening. TJ3AY, I think. No, TJ5SN. The band opened from the United States into Africa, Central Africa. And he worked dozens of stations in the United States at about 4 to 5:30 in the afternoon on the East Coast, and extended into the Midwest. So that's F-layer propagation on 6 meters. During this sunspot cycle, other than TEP, there have probably been only a few days when F-layer propagation that was not TEP occurred. Transequatorial propagation enjoys the special benefit of very intense direct radiation from the sun near the equator, and you get some real enhanced days of transequatorial propagation. So if we discount that and just look at east in the last sunspot cycle, JA's F by F layer